All right. First of all, I put up a link. I've been playing around with recording the classes recording my lecture. So you can go back here for going back to lectures we've already had. I am debating on how long to wait before putting them up there so that it's not just in lieu of going to lecture. So if I see a lot of hits to this page and not a lot of class attendance, I'll delay longer. Okay, so because you can't ask back, you can't answer questions over a recording. So you do need to go to lecture. It's really just so you can go back when you're studying or doing homework and things. For going back. Sure. These are just quick time movies, and they should play. Yeah, depending on your plugin, it should stream. Like it should play it as it downloads it. This one apparently does not play it as it downloads it because it's downloading it kind of right now. But if you get latest QuickTime, I think it should play it in your browser. If it plays it in a plugin instead of downloading it and then playing it. It streams on my computer. So. The other thing is in the discussions, I've put up a topic about for the project. So you can kind of post up topics that you'd like to do, and we can kind of discuss on here whether or not I think that can make a project. In other words, if there's enough content there that you can do a successful project with it, or if there's too much content there that I don't think you'll be able to really explore it in enough depth in the time period that you have. Okay, so and then I put up a post that has some basics on the project. The projects are going to really explore just find a specific issue in operating systems and explore it in depth. Okay. I'm not asking you to generate new novel knowledge on the concept or on the topic, but since you'll probably be taking a topic that kind of has been explored before, I need you to be able to illustrate it very well. Okay, so in other words, you may be taking something on scheduling, and you may be exploring something that's actually well studied in scheduling that previous research has a lot of knowledge on the subject. But I want you to be able to put enough together to explain that topic very clearly, so that when you do you're going to do a presentation, and then that presentation, we should walk away understanding the topic that you explored. Okay, so how do you illustrate a topic? How do you explore a topic? Well, typically you're going to be doing that through some sort of experiment or simulation or something of that nature. Okay, so the project will involve you writing a program, more than likely. Let me put it this way: the less that you do of programming for your topic, the more you'll have to probably do of research. So usually programming is more fun than researching. So I expect more people to do programs and simulations rather than surveying research. Okay. So the actual kind of deliverables for the project are going to be a paper. I say around 4 pages in length. I'm not really concerned with the length. I'm really concerned with whether you cover everything that we need to cover. I'll post up some kind of outlines of what I expect on the paper, but a typical paper is going to introduce and describe the topic that you're exploring. Okay, it's going to typically have some discussion of how you went about exploring that topic. In other words, if you're writing a simulator or something along those lines, it'll describe how you created the simulator, what kind of assumptions you made, what kind of things you did in your program to make it correct, exhibit the behavior that you're exploring, and then some results, usually in the form of graphs and things that show kind of what happens when you change these parameters or change this approach and the results. And then finally some sort of conclusion or and discussion, kind of summarizing what you've seen and everything, what you've discovered. Okay? So that's the typical form of a program, of a paper. It's going to have the supporting materials. So in the case of writing a simulator or something like that, your simulator is the supporting materials. So I want to see that as well. A slideshow, or if you have some other alternative presentation method, you can use that as well. And then an in-class presentation. So that's kind of the whole project piece. Okay. Some of the topics I put up here are mostly just topics from your book that we'll be looking at throughout the semester. All of these have a lot of different kind of potentials for project topics. A good example is scheduling that CPU scheduling that we've been looking at this week, right? We've already seen kind of something along the lines of what a project looks like with some of the scheduling algorithms, okay? So the scheduling algorithms are kind of, oh, here's a problem, it's CPU scheduling. We need to be able to put tasks onto a CPU and run them, and we want to do various things like minimize wait time, maximize throughput, and all these other kind of metrics that we want to optimize, right? So then we go through, and for a project, you'd probably pick one of them, right? Like you'd say, I like this round robin scheduling. Okay, so I'm going to look at round robin scheduling. So that doesn't mean you can just throw away all the other scheduling algorithms, because mainly you might say, well, I want to compare it to some of these other scheduling algorithms in terms of response time, right? So then you can write a little simulator, like you code up some Java that says, here's a list of tasks, and here's their arrival times, and here's a little thing that will grab stuff from that queue and process it using round robin, right? And then this other simulator is going to do it with shortest remaining time first, right? So it's going to do those two algorithms, and then you'll see kind of what the output is. Your output might be average wait time, right? Your output might be average response time, right? And then you'll start seeing things from that, like shortest remaining time first is best in average wait time, right? And then round robin will probably be better in average response time. Okay, so that kind of mapping you can start building a graph of. You can show, like, well, with jobs that average this long, then this is how the response time is. So you'd make a little graph. So we saw some of the graphs in the slideshow yesterday of, kind of what happens depending on factors that you change, like the time quanta and stuff like that. Okay, so then you run your experiment, you make fancy graphs and everything, and then you put together some slides showing that. Okay, you're going to discuss both the topic, what you learned, and your evidence, and then you can also do a little bit of discussion on how you did your simulator. Okay, because one of the big parts of researching these issues is the fact that you have to prove that your simulator or your model, your approach to looking at the particular topic is correct as well. In fact, sometimes that could be the whole aspect of the research, is proving that your model is correct. Okay, so there's going to be discussion on kind of both sides, but that's the idea here. And there's some other issues. Kind of one really open-ended area of study are issues specific to existing operating systems. So looking at issues in Windows XP or Linux or Unix or or Mac OS or any of these other operating systems. You can look at various topics there, but those topics need to be at the operating system level, not, Microsoft Word keeps crashing on my computer and that's my research topic, right? You're going to be more along the lines of, for example, we'll look at specific issues in scheduling in Windows XP today, but issues like that. So that's kind of open-ended as well. One of the big things today is that since there's Linux out there, Linux is actually a huge um, kind of easy way to research operating systems. You have a full-blown kind of enterprise scale Unix that has all the source code available to you. And then also, even more than that, is the development model is all open to you as well. You can read the mailing lists and stuff that the actual developers that are creating Linux are using. If you want to know an operating system issue with Linux, you can just go to the kernel development mailing list, pick any random mail, and you'll probably have a topic of operating system development right there, right? Also, Linux, since it's kind of a little bit more, it's not as rigid in its development model, has gone through some radical changes. Like in the latest version, like in the last couple years, they made a radical change to like the scheduling model that the scheduling that they use in Linux. You know, they make very drastic changes in how they handle symmetric multiprocessing and stuff like that. Okay, so that's what's going to happen there. Questions? What's that? Yeah, I mean, there's not much else here except that it's a lot prettier. It's basically along those lines. I'll post up more information here as I you know, just to clarify things as we go on with this. But if you have some ideas of what you want to do, go ahead and post them in this thread so that you can so I can kind of say, hey, that looks like a good topic, or you might run into issues here. You might want to change it slightly like this. Okay. For these, the presentation is going to be. I'm going to want the slides, your presentation materials, kind of at the beginning before any of the presentations start. Okay, that way everybody's kind of due on the same day. But then your presentation is obviously going to be on your scheduled time, so I'll probably randomize and then put them on those last couple days that we have in the class. Okay, and then the paper and deliverables will just need to be due end of the semester. So in other words, I guess on the final day. I might make it before any of the finals start so that I'll have time to look at them all and grade them. Okay. But then you run into some logistical issues in that your simulation code's probably going to have to be done well before you do anything else, because you're going to have to run experiments, gather the data, and then make fancy graphs and put them in your paper, as well as have some of those graphs ready for your presentation, right? So that you can put them on some slides and show them to the class and kind of illustrate what you're talking about, okay? So obviously that means you should get done a lot sooner than the due date. But as long as you have everything ready for your slides, as long as you have the data ready for writing your paper, you can do it however you want, okay? The other thing is that if there's a lot of issues, obviously the later you wait, the more busy we'll all probably be for, you know, like if you need assistance with issues you're running into. As far as the simulator and stuff goes, I don't really care what language or platform that you create these in. I am interested in your source code and everything so that I can see it and see how you did things and verify that what you're, you know, something that you say in your paper matches up with something that matches up with the program that generated that data. So if you say that your model assumes this, and then I look in your code and it looks like that assumption is actually implemented differently in your program, then, you know, obviously you messed up, right? So I can catch that. But if you need help from me, as far as while you're writing it, and you say, well, I run into this issue or that issue, most of the kind of just general programming stuff I can help you with, really, no matter what you do, as far as language goes. When it starts getting into specific things, I don't know. I do like if you go something very outlandish, like I'm not very good at functional programming like Lisp and things, but I don't know if any of you do Lisp. Most other procedural languages and object-oriented languages I'm very familiar with. I do a lot of C, C++, Java. I especially do a lot of Python. I dabble in Perl and C# and stuff like that as well. So
you don't mind, like, you can use like Visual Basic.
you can use whatever you want. Visual Basic. You can use Perl. You can use anything that processes your input and generates good data. So you can do it in whatever you want. And in fact, I recommend you do it in something something fairly high level, something very rapid, something that you can develop in quickly. Whether that's a rapid application development language like Visual Basic or some of these others, or it's just something that you're just very good at. If you're very good at a particular language, I don't mind if I'd recommend writing it in that. Because what you're doing here is you're not really writing very complicated programs. You're really just writing programs to kind of, express your intuitions of what happens with particular phenomena. So, write whatever comes easy to you. Okay, and it also keep in mind that you'll probably be tweaking, just changing little things here and there while you're writing it, right? As you start running the simulation and realize, oh, I need to, account for this, so I'll add in a little change. So I'd keep that in mind while you're writing. And in fact, in general, in programming, computer science, I'd recommend you develop a skill where you have a language like that, where you can quickly prototype and develop and check something, okay? Because it becomes a very powerful tool. Like for me, that's Python. If I need to figure out anything, I'll write it in Python very, very quickly, run it, find something out, and then if I need high performance, I'll eventually port it to something else, like C or C++. Okay? Or if I need it in a particular language so I can use it with some other tools, like if I have a library in Java that I need, I'll port it to Java. But I don't know. I'd recommend developing that skill of having a language of choice that you can quickly prototype and do small experiments with. Alrighty. We had left off where? And at the beginning of multi-level queues. Okay. So, are there any questions on the basic algorithms? Yeah.
Yeah, I can look at this here. It said that the formula that I want is like T plus 1.
The T and tau?
Yeah. Yeah. The alpha Tn.
Mm-hmm.
Okay. To me, I mean, if it's like based on the previous history, on the process run already.
On this process running. This history is the bursts of CPU that this process has used or is currently using. Because the idea is this: you have a process that runs for a long time. Okay, within those times there are these shorter bursts of utilizing the CPU. Okay, so I might run for for 10 seconds. Right? But in that 10 seconds, I'm not always using the CPU, right? Chances are, scattered throughout that 10 seconds, there's various times of I/O, of idling, and things like that. So, but within that, there are these bursts of using the CPU. This formula, this formula right here, these two factors, and then the formula combined, what they're meant to do is look at the bursts that have happened and keep track of them so that it can kind of predict what bursts will look like in the future.
Yeah, I mean, that's the point. Is I mean, if the process comes even a lot longer than that, how it can be set up in scheduling? I mean, it depends previous history usually, and previous, as you say. Now, a new process comes.
And we don't have any history on it. Okay.
So how that going to figure it out?
You just guess. You can just have a default initial burst time, and then this formula will make it change as it goes on.
So when it's running, let's say that it already allocated some timing for the new process came. And in the middle, the time is out. The process is still, am I making it clear? The process is lot longer timing than what it predicted.
Okay.
So when time is out, what happens to the process?
When the time runs out? In other words, when the time slice runs out?
Allocated time, right? Like 24.
Whatever,
Yeah,
nanoseconds,
yeah.
milliseconds, whatever.
But the process is still longer than that. What happens in that case?
Well, we'll stop it and run something else and then come back to it. But we can still track how long it took overall, right? I don't see what the problem is.
Okay.
Do you see what I'm saying? It's like if it's going to burst for, I don't know, for 50 time units. If our time slice, our quanta is still 10, right, is 10 time units, we can still see it over all 5 time slices that it ran.
Right.
Do you see what I'm saying? In other words, we can still measure it from start to finish.
Since it's running, what happens, or maybe, I don't know if I got wrong, that when it's running and if the time slice is wrong, what happens to the process? It stops there and switches to another process?
Yeah.
And then this goes on the queue or ready time?
Yeah, I mean, this is all happening with regular, we're switching processes and things.
Okay, I'll probably have to class.
But remember, I mean, the main, no, this needs to be resolved before we go on, because, I mean, this is the fundamental reason that we're doing these algorithms, is we're trying to determine what to put on next, right? So, this formula is how we guess what to put on next, but just because we determine what to put on next, that doesn't mean we can stop servicing everything else, right? So if we stop it and switch to something else, there's still that history and there's still that priority and things based on how much it bursts, and then that'll just determine kind of when you stop it, put it back in the queue, of where it is in the queue for when you rotate through and get something else. Now, the other thing that comes up is for some of this, those bursts, depending on how our scheduling works, we might not stop it at all. Okay, in other words, we might let it run to completion of the burst. Okay, like for example, we saw 2 versions of shortest job first, right? We saw shortest job first, and then we saw shortest job first with preemption, right? So those are 2 different variations. So this type of, history tracking, right, with the shortest job first with no preemption, right, we might predict, this one's going to have a 10 time unit burst, but it may end up being 60. But we still just have to wait until 60 because we can't preempt.
Yeah, that was my question.
Okay, in that case, we just guessed wrong, right?
Yeah, that's my question was that what happens to the process? It goes back to queue or is run all the way at the end?
Well, that's a separate issue, right? The separate issue, because if we can preempt, then what do? Well, we preempt it. We stop it and do something else, right? If we don't preempt, what do? Nothing. We wait. Okay? Is it all right that we guessed wrong? We don't have any other. We don't have a choice, right? If we can't preempt things, we have to run to completion, and there's no way around it. Eventually, that job would have had to run all 60 time units anyway, right? We can't perfectly predict the burst, though. In fact, this formula is very, very simplistic. Okay? In computer science, we have tons of better ways to do something like this, like predict based on previous behavior. We have most of computers, huge areas of computer science is looking at previous results and guessing what future or new results should be, right? We have genetic algorithms, we have neural networks, we have, support vector machine. We have all kinds of learning technologies in computer science, right? Why aren't we applying them to this? It's too hard, right? If I'm going to sit there and run 1,000 generations of a genetic algorithm to determine how big your next CPU burst is, First of all, the only job you'll be running on that computer is the genetic algorithm that I'm using to predict that. Another thing is the person running the job probably is done and tired of waiting for your computer by the time you can schedule it, right? So this will be wrong a lot of the time. Okay? Hopefully it'll be right more than it is wrong, and hopefully that the times it is right will create performance levels that are acceptable to us. Okay? The other thing is that while this is nice for kind of subtly tweaking what priority you put things at, we already saw the distribution, right? Chances are most of these are going to be short, right? So if your guessing algorithm is just guessing it'll be short, you're still doing pretty well, right? Because whenever you hit those longer burst times, it's not going to happen very often, and you'll just take a hit just then. So even though this is very simplistic and can be wrong, the problem's not that complicated.
What's like an acceptable range of error for the guess?
For the guess? Well, I mean, it's not alone. I mean, the range, the acceptable error on a formula like this isn't in a vacuum, because if you're guessing wrong by even a little bit on all the short jobs or whatever, but you're very exact on the long ones, you're not helping out much, because like we saw in the graph, like 80% of the jobs are short ones. So I think really just having a more coarse idea of whether this is a short burst job or a long burst job, I think would be acceptable for a formula like this. In other words, being able to keep a handle on a job that is CPU bound, that has a lot of long areas, if this can kind of say, well, my values are usually pretty high on CPU bound jobs and very low on lower bound, on IO bound jobs or interactive jobs, then that's a good level of error. Even if the error is like huge, if you can categorize it into two different areas, you're doing pretty well. We'll see in multi-level queues, okay, and what we're about to go over next is that this only has to be as accurate as the number of bins you have, really. Okay, so if I have 4 different bins for how I'm going to schedule jobs with different kind of performance, then something like this, where you're trying to gauge whether or not something has long or short bursts, just has to be accurate within 4 bins. Okay, and if you occasionally throw one in one bin rather than the other, it's okay too. Okay, so I guess the answer is not very accurate. The error can be actually pretty large, as long as it's not so large that you're throwing CPU-bound jobs into the IO-bound queue and IO-bound jobs into the CPU-bound queue. Okay, but again, these types of heuristics, they're not as exact as what we're used to doing with algorithms and things like that, right? They're more rules of thumb. Okay, and just real briefly, just to show you how everything fits together, it's like we have that formula, right? The prediction of CPU burst time. We have the algorithms that we saw, like shortest job first and things like that. And we're going to see these queues and everything. All of them are kind of independent. Okay, so that CPU burst prediction algorithm, you can use that with any of the other scheduling algorithms, right? And any of these scheduling algorithms you can use with any of the queues that we're using. Okay, and any of the queues we're using could use different prediction techniques as to what the bursts are. Okay, and we'll see that we combine all of these together. So, for example, like with the CPU burst prediction, what do we do when our prediction's wrong, or if we exceed what our prediction was? Well, it depends on all the other factors, on the algorithm or whatever. Sometimes we just let it run. Sometimes we can preempt it. Okay, so multi-level queues. The idea here is not to just use one of these scheduling algorithms or just use one of these prediction techniques or prioritization techniques. Because chances are, on a system that we're running, there's varying types of programs that run, right? And each of them kind of would prefer a different style of being scheduled. Okay, we've already seen that one scheduling algorithm that can minimize wait time isn't necessarily the best one for minimizing response time, right, or completion time, or any of these other factors, right? So we have a ready queue, right? And this is the queue that we're pulling from to schedule onto the CPU, right? What we do is we break it into multiple queues, okay? We have, and then they give an example of like foreground and background queues, and you'll find that in most of these queuing systems, right, that all of them kind of have this real coarse separation of interactive versus batch. Okay, what do you think they mean by interactive jobs? Right. So usually a user is sitting there giving input and receiving output, and there's kind of a cycle that's going between the user and the program. Well, what do we know about jobs that run like that? A lot of downtime. So the downtime is doing what? Why is there more downtime? Waiting on the user. So in terms of the system, we're waiting on I/O, right? On input/output. Input for, we're waiting on data from the user or giving data back to the user. So these processes are I/O bound, right? In other words, I'm going to spend more time waiting for I/O than I am on the CPU. Okay? So that leaves us with batch jobs. What do you think batch jobs are? CPU bound, right? So the other one's I/O bound. CPU bound is left, and batch jobs are usually these CPU bound jobs. What does that mean? They're not going to spend a lot of time waiting for user input or printing out user output so that they can read it on the screen. These are going to be jobs that sit there on the CPU and calculate and calculate and calculate.
Example on that one, like we always say, like we have an index in front of us.
All right, you are compressing a home video that you record. You recorded a home video, you load it on your computer, you cut out all the boring parts, put little fancy titles on it, and then you want to put it on a DVD so you can mail it out to people so they can watch your vacation at the beach or whatever, right? So you need to transcode that from the raw DV that's on from your video camera, and you need to transcode it into MPEG-2 for a DVD. Well, sitting there and taking this whole file and re-encoding it into a different format, you're going to use I/O so that you can read stuff off the disk, but chances are you're going to load big blocks into memory, and then you're just going to go through every frame and compress it, re-encode it, and then put it into this new format, eventually fill up another buffer, and then write that down to disk. But you're going to sit there for minutes and minutes just churning through all the frames one by one. Right? So that's a CPU-bound process. Now, some of them might have some sort of feedback to you, like a status bar saying how long it takes, right? And that is I/O, but it's not really a lot of idle time waiting for I/O, right? The time you spend waiting for I/O is really just the time it takes for you to write that stuff on screen or load it from disk. Right? What's that? And it's all O, with a little bit of I loading it from disk. Right? But both of those, you're not waiting on a person. See, people usually add the biggest latency in a computer system. Right? They also add most of the problems to a computer system. So each queue has its own scheduling algorithm. Notice what they do here. This is just, again, an example of how you could approach this. You have foreground and background. Notice they put foreground round robin, right? Background first come, first serve. Why? Round robin is you service for a time quanta, move to the next one, service for another time quanta, move to the next one. So why choose two different scheduling algorithms there?
Foreground has a
Right. So how do we keep the user happy by using round robin? Which of the kind of metrics are we working with there? Right. So response time, right? We want the user to be happy by making it so that everything that they do, the computer can react to and give them, if they click here, the cursor moves down there. If they start typing, they see their characters on screen. Nothing's worse than if you're sitting there working in if you're working in a word processor plus you're watching a movie or something, and your computer gets bogged down, and you start typing, and it takes a while for the text to catch up, because then you're kind of disoriented as to, what has it gotten, what hasn't it gotten. So response time is key there, right? But on the other hand, if it didn't do that, then your movie would be skipping, and some of the frames would be out of sync with the audio. So all of those things I need response time more than anything else. Okay. Well, then why run the background in something like first come first serve?
It's not as important to the user.
Right. So what are we doing instead? Right, since nobody's really keeping an eye on it, it doesn't matter when it gets done. But what is the biggest drawback to something like round robin? Turnaround time is one of the big things. But what else are we doing? What is unique about some of these things that we saw, like first come first serve, the first version of shortest job first? What's really different about them and round robin? And then also, okay, and here's the one that gives it away. The second version of shortest job first that we saw. What was the second version of shortest job first? Preemptive. And the original one was just shortest job first.
Round robin doesn't matter. It's socialistic, I guess.
Everybody gets
Everybody
like, no, but there's one big issue. And what gives it away is there's shortest job first, and there's no preemption. Okay? How could no preemption, what does that mean? Obviously, it means that our response time isn't going to be as good for the one without preemption, right? But what does preemption add?
Just the shorter burst time, quicker.
Maybe, maybe not.
What's the point of getting?
Depends on how small the quantum is. What?
What's the point of getting first?
Well, we've already seen that it's the optimal solution for wait time.
I mean, if you're doing the background anyway, and you have like 5 programs, one it's going to take.
Well, there's still, completing these jobs is still important, right?
Yeah.
And completing them shorter.
If one's going to take 50 times and one's going to take 10, it can take 60 either way.
Right, but what if I'm the one using the one that has the 10? If I need the data from the one that's 10 times.
You're talking about PC. Like from opening a zip file.
Okay, that's fine. That's fine that you can say that. Yes, in some cases it won't matter. In those cases, we don't have to study it, right? Because it doesn't matter if it doesn't matter when they get done. But that's the thing is, yes, looking at the completion time, right? The average completion time. If that's your only concern, both algorithms are equivalent. Okay. And I don't mean both of those algorithms. Both algorithms of first come, first serve, or shortest job first with no preemption are equivalent. Okay? But I want to get back to this issue of the idea of what is the biggest trade-off with preemption?
Longer bursts have to keep waiting.
They may, depending on, no. I'm serious here because they may have to keep waiting, but that's more an issue of the specific algorithm we use. Okay, what I'm getting at is preemption itself. What is the trade-off with preemption? No, we still have those algorithms that you choose. Those are separate, but overhead, the switching. Okay. Any time that you preempt, you have to stop a job, save its state, switch to the other job, load its state, and do that several times throughout the job. Okay? First come, first serve, or shortest job first without preemption. What do they not have that something like round robin almost definitely has? Overhead of context switching. Right? They have preemption. Okay? Preemption adds to the utilization of your CPU, right? Increases your run times, reduces your throughput by adding in work that is not furthering jobs. Okay? That is the key aspect. All these other things we were talking about, well, some might complete before others and things like that. We don't know that if all I'm asking you is what about preemption? Okay? Huh? Yeah. Whenever you have preemption, the context switching, okay, that is wasted work. Wasted in the sense of factors like throughput, job completion time, okay? All of those you're adding in time to do the preemption. Now, why do we do it then? Well, because it's helping us, right? That additional wasted work is helping us in terms of response time and things like that. It may help us with things like wait time, right? Because we noticed that shortest job first with preemption had shorter wait times than shortest job first without preemption.
It's important also because if there is no preemption, then you probably want to run for suppose 1 hour.
There's all manner of issues on whether or not you should preempt. Not just that. I mean, that's the thing. That's a huge issue is what's going to happen. So, you'll notice none of this stuff we're talking about, we don't just say, oh, this one's better, right? Or this scheduling algorithm is better. Or this way of doing queues is better, right? Because all of them are trading off something. In other words, if you got into the book as one of the entries for a scheduling algorithm, chances are you're best at something, right? Because if something's worse in all cases, don't put it in the book, right? Don't study it because, you already know, coming up with useless scheduling algorithms, we could sit around all day and do that, right? I'll do the one that has, I'll schedule all the jobs that start with A first, or something like that. Something completely off the wall. But all of these have some sort of benefit, okay? So the idea here is the background, maybe we can do something where we minimize that overhead of context switching because, why? Because we're not as concerned with the major issues that it addresses, and that's usually wait time and response time, okay? But the foreground, we're not really concerned with when stuff gets done or the throughput of jobs going through the CPU. What we're concerned with in those cases are what's the response time and what's the wait time. Maybe. I mean, foreground is just a general term. There may be kind of more detailed ideas of foreground, like the window that's in front of all the other windows might be the foreground window, even though all of them are considered foreground in the overall sense of the jobs.
If I have like 10 windows open and there's one on top, which window is it doing?
Well, then in that case, if you do have the concept of foreground window as opposed to the others, you'd probably make another queue. Do you see what I'm saying? This is a general idea of there's differentiating between foreground and background. You can make even more specific generalizations, but you need some way of addressing. You're eventually going to get to, here's the foregroundest application I got, but you still need to address that there's all these other categories and how are you going to service them? Okay? Because you can always easily get to a point where you have something that's the biggest priority and you're going to give a time slice to that. But you eventually have to get to the point where you're time slicing the lesser priorities. Otherwise, we lead to those situations of like starving out other apps. Okay? But you'll see that this is the basic, is just having 2 queues. But you'll see that some of the other, like all the others, like in Linux, there's hundreds of queues based on individual priority levels. Okay, so that's a big part of these multi-level queue approaches. Okay, between the queues, we can have fixed priority scheduling, service all from the foreground, then from the background. Right. In other words, as long as there's foreground, we'll service those and not get to background until they're empty or all idling, which is possible, but we do introduce the possibility of starvation. In other words, if we get enough service requests from foreground jobs, there's a possibility that we'll never get to some of the background jobs. Okay? You can time slice. Each queue gets a certain amount of CPU time, which it can schedule amongst its processes. For example, 80% to foreground and round robin. So that kind of time slice, that's another level of time slice. In other words, sure, when we're on there scheduling individual processes on the CPU, we might be using time slices to give them those. But this is a higher level where we'll say, for this time slice, this larger time slice, I'm going to run round robin on the foreground queue. But then, once that's done, I'm going to come down here and run another time slice of first come, first serve on the background queue. Right? And then I'm going to come back and time slice the round robin. And you might make it so that the round robin time slice is big and the background time slice is small. So in that case, this 80% of your time is up here and a smaller percentage is down here.
So what really constitutes foreground and background? Like, I still understand. Like,
we don't know yet. Each operating system has a different way of categorizing these things. For example, we'll see examples of one that will track how many times you're waiting for I/O. Like it might, and it might differentiate between I/O. Like if you wait a lot for disk I/O, I might put you as less interactive than somebody who waits a lot for keyboard I/O. So that's the big problem with a lot of this is even though we might create neat algorithms that can schedule all these different queues, how do we put them in the queues? And how do we determine what to put in those queues? And also the fact that these queues can be tricked. We'll come up with some examples of that.
the best, like, so foreground and background actually around, like, I could assume that one of them has a like higher load path, such as like you know, like higher computation, like during the kernel or something, and like the other one is like user Windows. I mean, I'm sure they can switch around, right? Whichever one.
Well, I mean, all of those, I mean, in terms of higher computation, what you're talking about is burst lengths, right? So, I mean, ideally, a perfect scheduler puts all the things that have particular burst attributes in the correct queue, right? So, for example, the best ones to put in the top are short CPU burst lengths. If you prioritize those highest and long CPU burst lowest, chances are you'll get better scheduling. You'll get better scheduling in terms of at least servicing everybody, nobody starves. You're getting very good response times. You're getting very good throughput and things like that. What's that? Variance?
Over here it says something like putting average and variance, like shorter one getting smaller time.
Well, with variance, if you have variance in the average times,
Right.
then hopefully you're a multi-queue system that can move queues. In other words, while you're on the parts that are long CPU burst, you're in a low priority while you're on the parts that are small. But I mean, the whole goal of all of this is to match up those burst lengths with the correct queue. Because if you can do that, what they're saying is that we've already seen the phenomena of why each of these does what they do best, right? The round robin gets good response time, and they're very suited to these short burst length jobs, right? First come, first serve. Because it doesn't matter, if you're not preempting them, though, you'll get more utilization and get those jobs done faster, better throughput, right? We want to also include in there wait time and that kind of thing. We could do shortest job first type of algorithms for the background, okay? But the thing is I know you're bringing up a lot of, well, here's a scenario where it doesn't work. Or here's a scenario where it's broken. Okay? Yes, all of these things have broken scenarios. Okay? The thing is if you want to bring up the broken scenario, you have to come up with a fix for the broken scenario given the information that the scheduler has. Okay? Or a way to ascertain new information. Okay? So those broken scenarios are what these are attempting to minimize, is that idea that we're not putting a bunch of long CPU burst time jobs in the interactive queue. Okay? All right, so here they're showing, right, a 5-queue system where they have system processes at the highest priority, interactive editing, batch processes, and then student processes. So they're just saying they have 2 different batch systems where, like this might be on a very expensive, large shared system, and they have a separate kind of class of user that they can put in another batch. In other words, the student users on this system only have access to this one particular batch priority. Yeah.
Also, when setting priorities, like wouldn't like let's say with first come first thing, you don't have.
Well, that's not setting a priority.
I know, but that's what I'm saying. Like, wouldn't that be more interesting due to the fact that you don't have a priority? Because
No, you do have a priority if you're in the first come first serve queue.
but like what I'm saying is like wouldn't it be easier for the computer to do whatever it wants rather than running an algorithm on the side?
Wait, what do you mean?
As in like it's gonna take more computing power to run an algorithm and decide which of these processes go and handle first rather than
You have to do something. I mean, you have to run an algorithm.
yeah.
So what I'm saying is, I mean, what do you mean by running another algorithm? Like,
As in like deciding which of these processes is gonna take the least time. I mean that takes computing power too, right?
right?
So why not
Why not care and just
yeah,
just always do first come first serve?
yeah, instead of like 60 time units, it might take 65 time units because you have that little 5 time units just to compute within these processes which is small.
Okay, but I mean, we've already said why we don't do that, right? That there's all these other factors of like for example, your approach will create less interactivity. It will create worse response times, right? No, I mean, that's the thing. It's like, yes, there's additional computation being done to do these other more complex algorithms, but the idea is that the time it takes to do those computations leads to a response time of X, where X is less than what we did with just round robin.
So it might be better to do. I think it might be better for mainframe to do. Because all it's doing is computation.
No, mainframes are also probably going to have interactive jobs as well. Like something like this. Like this is probably a mainframe, right? A big time-shared mainframe. In fact, I mean, actually, it could be argued that going to the lower end, the PC, where there's only one user, that you can just say, well, always service the foreground job, and then everything else is less. Okay? No, but what I'm saying is yes, that is a big issue, is what if doing all these computations to determine what to run next takes too long, right? So when you brought that issue up, that doing all these computations, you have this 5 time units to determine what to do next. What is the trade-off there? What was your complaint about the
fact that you have to use CPU time to do something.
I understand, yeah, but what metric does that match up with? In other words, what metric are you complaining about that we're increasing or making suboptimal by doing this? Right, well, throughput, right, the throughput. Okay, now this is important. You were saying that doing this is you're damaging throughput. And I agree, you are damaging throughput. But what are you? If we're not doing something better in something else, then we shouldn't be doing it. Right. So we might be. What we're saying is that response time is getting better, right? So what we're saying is the amount of damage we do to throughput is worth the benefit that we have to response time. And wait time probably.
So I guess it would also depend on the number of processes you're running. If you have like 800 processes running, it would take
There's
longer.
so many things it depends on. All of it depends on all that, but you need to talk about it in terms of which of the, see, you have to look at these algorithms, you need to look at these queues, you need to look at these prediction methods, and you need to look at them in terms of which metric do they benefit, okay? Then you say, okay, here's the metrics that these particular approaches benefit. And then you go to a computing system. You say this computing system has this many processors, it has this many users, they run a mix of applications that have these, they're interactive or they're not interactive or whatever. And then you go to your list of approaches and you say, oh, this approach is best for this system because it minimizes or optimizes this particular metric that those users are interested in. Okay? But to try and look at these techniques and say, well, obviously there's a drawback, it's no good. We should do it this way instead. We can't do that in a vacuum because all of them will kind of see something, oh, one's better at this and worse at that. Okay? All of these metrics are in conflict with each other. Okay? Some of them are complementary, some of them are, are in conflict. So you need to find out what the trade-offs are, and then you choose the trade-off that benefits your user, your particular system. Yeah.
So in a multi-level queue system, I guess, the CPU is going to be time sliced somehow, probably.
Maybe, depending on how you're doing
Okay,
it.
but say it is time sliced.
Mhm.
Fixed length of time for every process.
Oh, for every queue or every process?
That's what I'm getting to.
Okay.
So, well, process in the general sense of it could be a queue of processes.
Okay.
That's no good. All right. So, anyway, there's a slice, and each slice is dedicated to a different queue.
Uh-huh.
And during that queue slice, it can run as many.
It could do them however it wants, yeah.
Okay. Okay.
In other words, the processes that are in here, these might be round robin sliced.
Right.
So in other words, when you get to your slice, we round robin slice this.
And the CPU can be sliced up however it wants to do it.
Right. And then when it gets sliced down, this one gets to its slice, it might not do any slicing. It might not do any task switching. It might just run directly through the queue. Okay? And just to add another twist onto it, this might not be time sliced through the queues. We might run all of these and never get to these unless these are empty or idle.
Is that all based?
No. No, how all real operating systems do it?
No. Like all like mainframe.
Well, you mean mainframe operating systems? No. All of them, that's your selling point of your operating system, right? Is any operating system that's created, you kind of say, ours is best, why? And one of the factors is scheduling. So all of them kind of differentiate themselves by doing different techniques. Like we've seen, if you look in your examples of your book, some of the good things are the historical anecdotes of this used to be used in this particular operating system, and here's a funny story about what happened. Like they have an anecdote in there about some system at MIT being shut down, and there was still a process that had never been serviced from 10 years before when the system came up. Okay, and it's pointing out they were using a scheduling system that has the possibility of starvation. In other words, that system serviced enough jobs that it never got to the lowest priority threads or priority processes. Okay, so a variation on just regular multiple queues is multiple queues where jobs can migrate queues. In other words, as the system learns more about a process, it can reclassify it into a different queue. Okay, so this feedback queue is you need some way of changing priorities on these processes, and hopefully that's based on useful information that you've seen as it runs. So we'll see that each different operating systems have different techniques on whether or not to move something in a queue. Okay, so multi-level feedback queue. round robin with time quantum 8 milliseconds, round robin with 16, and then first come, first serve. So this first come, first serve queue is, obviously some sort of batch queue. They're saying that's not service with first come, first serve. Okay. This, I think, is where service, this should be round robin. Sorry. They're saying that this round robin is done first come, first serve. So you get into the queue and then you'll be served in round robin. So they shouldn't use that term there because it's confusing with the other one. But what they're saying is you get into the queue and you're put into the circle that's being served as round robin. And it says, okay, you get 8 milliseconds. If it does not finish in 8 milliseconds, you're moved to Q1. In other words, you get 8 milliseconds. If you can complete everything that you need to burst for in 8 milliseconds, cool, you can stay in this queue. In other words, if you run through some computation and then wait for keyboard input, if you do that within the first 8 milliseconds, I'll leave you there. Okay? If not, in other words, if I have to preempt you, I'm going to move you down into Q1, where now your quanta is 16 milliseconds, but you're a lower priority probably. So in other words, you're going to get the CPU less, but when you get the CPU, I'll give you a longer quanta. In other words, a longer time period. Okay? So you're serviced again, and you receive 16 milliseconds, and if you don't finish in that burst, I'm going to say that you're non-interactive and move you down into first come, first serve. Okay? And then in this, they don't really show a method for moving back up the queues. Okay? But yeah, exactly. Penalized in the sense that you're not going to get the CPU as often, but you might be getting it longer. So in other words, you're being penalized in response time, but you might be rewarded in throughput time. Right? Because as you move down to these, what do we notice about these? The overhead in these queues gets lower as you go down. Right? Here you get the CPU more often, but you have to stop every 8 milliseconds and go through a context switch. Here you get it for a full 16 milliseconds, and then you take the hit. Here it might be very, very long times that you get, but only when nobody's using the system. In other words, if the system's idle and there's not anybody sitting at the terminal, you may get the CPU for just until you get interrupted. They might just let you sit there and run. Okay, that's the idea behind these batch queues were often kind of prioritized jobs so they could run like at night when like nobody's on the system, and that way they could just run for as long as they need until they're done. Okay, but in our case, it might be when a user is sitting back like this and not typing anything in a program, or they left the computer idle. Yeah.
So all these queuing systems, they're all in the kernel, right?
Some microkernels will put some scheduling stuff outside the kernel, but yeah.
This is hardware based, right?
Oh no! This isn't hardware based. And I don't know. Some of it might be hardware assisted, like things like context switches and stuff like that. And chances are, any operating system that does this is going to write in the context of different hardware platforms. They're going to do it, but for the most part, it is outside the hardware, and that's actually fairly good that it's outside the hardware, because again, different uses of systems have different metrics that they're trying to optimize, right? So each of these you can change these techniques. And some of them are even so far out of software that you can actually, it's an option on your system as to which scheduling mechanism to use on a system. So you can tweak things, or even tweak parameters of the scheduling system. Okay. So that's the idea of moving queues. And here's just a silly diagram of jumping through the queues. Multiple processor scheduling. It gets even harder at that point, because now you have multiple CPUs that could be servicing jobs, so they can actually be pulling from the same queues at the same time, and how you approach that can also change uniquely for multiprocessors. One of the biggest things that comes up with multiprocessor scheduling is the concept that you actually take an additional hit by moving a process from one processor to another. Okay? One of the biggest hits you get is the fact that now you're using a different cache at that point, right? If you and a couple other processes were running on one CPU, switching between them, chances are you're all loading different things in the cache, but your pieces might still be in there, right, as you switch. You move to another process, that process is kind of clean as far as you're concerned. None of your pages are in there. So you have these additional hits. So one thing that you can do is you can have processors, have processes, have processor affinity, which means have a processor prefer certain processes so that they'll kind of run on the same one if they get scheduled. In other words, an additional scheduling problem is I'm in the queue, I'm the next one up to bat, but my preferred processor isn't there. You have to make a decision. Even though I'm ready and I'm the next one in the queue, should I wait and let somebody in front of me in hopes that my preferred processor frees up? So that's just another level of decision making that the scheduler has to make at that point.
I mean, like in a PC, right? You have certain things like a video card, right? It has a separate processor on it. I mean, so like same thing.
No.
It's not.
Because the video card is not being put into the pool as a... In other words, you schedule the video card separately because it's not... What we're talking about here is just scheduling CPU time. The video card at that point, even though it has a processor, is just I/O for the most part, right? But how you schedule the video card might be, I don't know, you might have its own separate scheduling algorithm. Okay. Now, if you do get to the point where some consider that like this scheduling the video card and its processor separately, some might consider that a form of asymmetric multiprocessing. So there's symmetric and asymmetric. But asymmetric and symmetric multiprocessing. Symmetric multiprocessing, right, SMP, okay, is when you treat all the different processors kind of equally. And then you just take a bunch of jobs, you take a bunch of processors, and then you just deal them out. Process on each processor, time slice, and then each of them swaps out with another job. It's symmetric because you use all the CPUs for all the jobs, right? And they're all equal. Okay? And hopefully they're loaded completely equally. Okay? Asymmetric multiprocessing is usually where you're going to have very, very specific uses of different processors for different processes. So like in some, like I think Solaris can be run in a mode where one of the CPUs is dedicated to operating system threads, and then user programs can go on others. You can also make it so that a database server runs dedicated on one CPU, and then other things can split up the other ones. But that asymmetric multiprocessing is kind of saying particular things will run on particular processors, and then you can mix and match from there. Okay, so the idea of like a video card, it has its own processor on it. You can kind of consider that asymmetric multiprocessing in that only jobs that have to that do a particular style of computation can be routed to the video card, but it's kind of done separately, right? That has its own scheduling, and then the general purpose CPUs have a separate scheduler. So in asymmetric multiprocessing, the OS CPU that you put in there might be scheduled in a certain way, and then all the other ones might be different. But they're really separate entities as far as the scheduler is concerned. Okay? I'm going to skip some of the threading stuff. We didn't go into detail in the threading, but for the most part, different operating systems have different approaches to threads on whether they schedule them like they do regular processes or if there's kind of a subsection that schedules them differently. Okay. All right, let's take a quick break, and then I'm going to quickly go through some specific techniques for operating systems. Okay, so let's take about 5 minutes or so.
Like 4 hours. Yeah, it took about 4 hours. Yeah. It doesn't know much. I'm pretty sure all of them notes. Online notes. Developed it. But it's like once you can do the personal problem, then you can go to the idea of the rest. The last part's really hard with that. Yeah. I mean, I skipped something with my everybody was comparing the last answer to something wrong, so I don't know what to get rid of that. Yeah, it was not right, so the only reason I get it is because this reception's really well. It's like one of these really helps. I have an internal one too. Are you getting wireless here?
Yeah.
The library still works. I guess since they're doing all that work, they might want to.
Apple seems to have pretty good antennas in their boxes. Alright.
Have you looked at the homework yet?
No, I haven't gone through them yet.
That took me a long time. I think I was like 2 pages over.
Oh, really? When you guys paste it in, did you cut and paste just into the regular text?
Yeah.
Okay.
Pretty bad.
Yeah.
Like mine wasn't even spaced or anything. I tried to space it out and it submitted it. It just unspaced it.
Yeah, I'm trying to. Did any of you switch to the HTML mode, the little Java applet? In the future, I think I'm going to recommend that because that will at least preserve. The only thing I really want to preserve are line feeds because when you paste into text, it removes all white space because it treats it like HTML. So anything that's white space, it'll ignore.
I can resubmit it.
No, that's right. No, I'm just saying in the future on the next ones, there's a little,
There's the HTML tab over there.
yeah, like a little. to like this HTML creator. Okay, and when you switch to this, you don't have to do any kind of HTML formatting or anything. But the main thing is that if you post multiple pieces of text, it'll preserve the line feeds. So that's all I want, are line feeds.
Was there any way we could resubmit it or something?
There can if I pass it back to you.
Yeah, we can.
Yeah. So I can go into your assignment and return it to you so you can do whatever and then come back. But I mean, I don't mind on the first one. But. Okay. So we'll take a look at the some examples of operating systems. So what we were just talking about before, again, are just the tools that the operating system has to schedule. But these are some specific examples of 3 different operating systems and how they schedule. So we can kind of see what each of these, how each of these approaches the problem of how do I service all these jobs for the type of user that uses my operating system. Okay, so Solaris has kind of 3 general areas that it breaks down into. I'm gonna get to the. They have some good examples. I think they have examples of the different. There we go. Okay, so there's actually 4 different classifications. These 2 right here, interactive and time sharing. Okay, those are actually put into the same kind of pool though. Okay, but within that pool, they have different priorities, and I think they have examples. Let me see. Nah, they don't have any good examples. Some of the others they do. Okay, but the idea here is that we have these different levels, and then each of these queues is going to be serviced in a particular way. So this is our multi-level queue that we saw from the general case before. This is actually how Solaris breaks it down. Now, each of these within here, they have different ways of servicing the jobs within each of the queues, and they have a complex way of migrating. Okay, they migrate these processes to different priorities throughout their run. Okay, now this priority here is the priority of the job. This is how big a time quantum it gets in scheduling. So the time quantum is the slice size that you get of the CPU. Okay, and we've already seen that the trade-off between the time slice sizes are usually shorter time slices is interactivity, longer time slices is less overhead. Okay, in this case, priority 0 is the lowest, and 59 is the highest. Okay, so they go. So the greater the number, the higher your priority. Now, notice what happens here. You're at a particular priority, and you get the CPU for a particular length of time. Okay, and then you can change priority based on what happened to you while you're running. So a time quantum expiring, this 30 priority gets changed to a 20 priority. So what has it done? What does this change from 30 to 20? What is that when the time quantum expires? Why? Well, this is how we're determining the priority. Why have we changed from 30 to 20? First of all, what's happened to the priority? It's decreased, so you're a lower priority on the system. In other words, you're not going to get as much service, right? Why lower its priority? We saw it in the example before. It didn't finish, right? So in other words, you could have had the CPU for longer, but I had to expire you. I had to preempt you. So, because if you would have gotten done with your CPU burst by then, right? In other words, went to look for I/O or slept or something, you would have stayed in this priority, right? But you expired your time quanta. In other words, you could have used the CPU more. I'm moving you down the priorities because you're less interactive. Okay. Now, return from sleep. If you were 30, you now become 53. Okay. What's return from sleep? You can also see this as return from wait. When does something go into the wait state? All of this is multiprocess. Waiting for IOs usually, right? If you make a system call to do input-output, you are put into a wait state. And then the interrupt from the IO coming back will kind of wake you up. So what has happened to the priority here? It's gotten higher. It's been increased from 30 to 53. Okay? Why? Okay, chances are you're going to want the CPU, right? You went and did I/O for a reason, and you're going to want the CPU to do something with that. What else do we know about you, or what else can we suspect about you? If you're returning from wait, what does that mean that you just did? You just did I/O, right? Well, what do we like about processes that do a lot of I/O? They have a lot of wait time, so let's give them more CPU because I don't have to really worry about them because they're going to preempt themselves. They're going to stop processing themselves going to I/O. Okay, interactive jobs. Interactive jobs we like on the CPU because they're going to stop on their own, right? They usually have shorter bursts. Okay, so that's what this dispatch table is pointing out is, first of all, I get smaller time quanta as I go up the priority queue. In other words, short little bursts of doing processing and then waiting, right? So larger ones down here, because if you're low priority, chances are you're CPU bound, and you're going to want big time quanta so you don't get interrupted, right? Less overhead, better throughput. And then we are going to move you up and down the priority queues, right? By pushing your priority down as you exhaust time quanta and pushing priority up the more you do I/O. That's a pretty good system, right? So what end up happening is you'll kind of be moved into the priority level that fits your mix of I/O and CPU, right? Because what is it about these smaller time quanta as you go up the priority? What's that? Yeah, smaller or highest, right? So if you have something where your CPU bursts in between I/O is 60, but otherwise you do tons of I/O, but your bursts are 60, where do you think you'll end up? Where? How high up? You'll probably end up in here. Why? Because if most of your CPU bursts are 60, you'll end up expiring more time quanta if you're put into this priority level, right? So if you're expiring more quanta, you'll be pushed down, right? You'll be jogged back up a little as your I/O gets done, but then you'll start hitting more quanta where you expire, and then, so in other words, you'll fluctuate around here, the interactive area, but you'll kind of tend towards this area. Yeah.
Can't you make all of those variable?
What?
Like all of like the quantum and stuff? Like what if all between? You know what I'm saying?
Well, the more variable you make it, the more. See, before you were complaining that we're doing too complex algorithms and we're using up all this time doing this stuff. But now, no, you could make this more complex. In other words, like make the quanta related to how long, you Like, I mean, are you saying like just have varying degrees of quanta?
Rather than wasting 20 time units, well, I just spend those 20 time units. Like a program only takes 60, right? Someone gets them in 80 or whatever. Rather than wasting those 20 time units.
Well, you're not going to waste 20 time units.
What do you do?
Because when you hit I/O, you're going to yield the CPU.
What if the program only takes 60?
That's what I'm saying. If you only take 60, you'll yield the CPU, and those 20 time units aren't allotted to you.
Okay.
The key here is that you're not being preempted. The CPU is not as concerned with you not using up time, right? Because if you yield using I/O, then you'll yield the CPU, and it could schedule something else. Okay. These time quanta are more concerned with if it doesn't yield, you have to preempt.
I understand the spread. The one is on
If a-
30, got already allocated time, quantum on 80,
Right.
and it's spread 20.
No, that's the new priority you get if your time quantum expires. If you're a 30 priority process, and you run for 80 milliseconds, and then we stop you, you'll be downgraded to a 20 priority,
And allocated time is like 20, right?
is 120. So what it's doing is it's trying to find a time quanta beyond what you normally need. Okay? Oh. If I'm expiring you, okay, if you're using time quanta and you're going beyond it, that means I have to stop you. I have to preempt you, right? So I have to stop you running. I have to save your state and whatnot, right? If you yield to me as a process by saying, I need I/O, right? I need to get information from disk or get information from the keyboard or put output out there, I don't have to do anything, right? That's better for me because if you're yielding to me, that's less work I have to do to determine whether or not I should take you off the CPU, okay? So what I want to do is get all my processes to a point where I'm not interrupting them, and yet I can still service as many jobs as I need to, okay? So if I downgrade you every time you exceed your time quantum and move you down to a priority that has larger time quantum, I'll either get to a point where I can't give you bigger slices, or I've given you slices where you're yielding to me more often than I'm preempting you. Does that make sense? So you're moving them down into larger time slices because the idea is that the larger your time slice, the more you can get done when you get the CPU and the less overhead of me swapping you out. Smaller time slices, I might preempt you more, but I can keep everybody happy by servicing more jobs and get better response time. So this moving people down when time quanta are expired, moving them up when they do I/O, I'm kind of finding your area where there's a good balance between how much time you get and my ability to move on to other jobs. Yeah, that's your slice size. Oh, no. Yeah, that's what's. This isn't time units. This is priorities, and this is priorities. These two columns are priorities. This is time units. So it's saying that after 80 milliseconds, your new priority is 20. Okay, so if your new priority is 20, you go down here, and now your time quanta is 120 instead of 80. Okay, the 30 priority, you run for 80 milliseconds or less. You can run less, right? But if you run beyond 80 milliseconds, your priority becomes 20. So if your priority becomes 20, your new time quantum is now 120 because of this line. Okay, so these are priorities. The last two columns are priorities. The second column is milliseconds.
How does the computer calculate how much time it's going to take? How does it know what quantum to put it in?
Oh, that's a timer. So it's going to say, that's hardware driven.
So it
Is
runs it first? It runs the program first and times it?
No, 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 no. That's how much it's giving it. How long it takes, we don't know. This is a way of guessing.
Are you asking what the initial priority would be?
Yeah, if I'm running like, if I just start a program, how would it know how long it's going to take? How would it know what quantum to put it in the first place?
That's what this is doing. It's finding the quantum to put it in.
But what if it's done before it doesn't know?
Then we don't have a problem because we don't have to schedule it anymore. Right? We don't know. And the thing is we don't know whether or not the quantum that we put it in is good or not. Because even though it might be 60 milliseconds for this particular burst, the next burst might be 20 milliseconds. The next one might be 200. The other thing to realize is that if this 30 level priority job, right, if it gets done in 60 milliseconds, what happens to its priority? No.
What do you mean it's done?
It gets done using the CPU. In other words, yields to the CPU.
Does that mean it's waiting on something else?
Yeah.
Because if it's done otherwise, then it's finished, right?
Right. Otherwise, it's terminated. Right. And then we don't need to do anything with it. But it gets done with its burst in 60 milliseconds. What happens to its priority? No, nothing happens to its priority. Because we haven't hit either of these events. Right? Now, in this case, when it wakes from that waiting, then it will get prioritized higher. Okay? But the key here is that time expiring, right, and a quanta expiring is an event. I mean, that's a significant event to the scheduler. It's saying that it didn't get done working on whatever it's getting done before the next I/O or whatever by the time that I've out. In other words, I guessed wrong. So I need to change the priority in some way. We can talk about this more. Let me just real briefly. This is one method, is Solaris's, okay? We also have a Windows priority. This is just a complicated way of assigning priorities. They have major priority levels of a job that are created, that are kind of determined when you start them, and then from there they have kind of variable amounts that you can have for each one. And some of these can be set manually by the user or requested by the user, and then the other ones are CPU based. I mean, that are OS determined. So what they're saying here is that these different priorities, right, they have a range that they are in for each priority. So they're saying that some might be high priority, but some are higher priority than others, right? So you can go all the way down to 11 for the lowest here. So some high priority above normals can actually be can be higher priority than a real low priority high. Right? So in other words, this 11, even though it's a high priority, it's still less of a priority than a time critical or a highest above normal. Okay? It's just a way of breaking up these numbers. These are more determined by, these are kind of things that users can request, like for their jobs. Like when you create a thread, you can say, I want a higher or lower priority in my normal priority system. So they're kind of just suggestions. Like in the task manager, you can go through and you can actually toggle those, and then those are these user configurable priorities. Okay, and they also warn you that you could screw up your system if you set the priority too high, because what you'll end up doing is, if you put a CPU-bound job real high, you'll end up giving it a bunch of slices, and you could potentially, if like real time, you could starve out other processes. Okay. They don't talk too much. Your book has a little more discussion about how Windows XP migrates jobs, but because XP is often very user interactive, they pay a lot of attention to moving processes to higher priority queues based on input output. So they do have techniques for watching, like you're waiting for a lot of disk, I'm going to put you higher than CPU bound but lower than something waiting for a lot of keyboard and mouse. Okay, so they're going to move things, and then also you have this concept that you can see in like your system properties where you say foreground and background, like where you can say prioritize foreground or prioritize background. That can also affect how you get prioritized when you start. In other words, jobs that you start that are actually running in the user interface and everything can get prioritized higher so that they can, since they're interactive. Whereas system jobs and stuff that you're, like system services that you're loading up, those can be pushed to the back so that they can get bigger time slices but don't have the user I/O. Okay, and then it's a setting because if you run a Windows box as a server, you'd want background priorities to take priority because you don't care about the user experience sitting at the console because nobody's using it. It's sitting in a rack in a server room, right? Whereas if it's your desktop, you want the foreground because you're going to be sitting there working with all the different programs. Okay, and then finally, Linux scheduling. They do this. They do a prioritization. They actually reverse the numbering. 0 is the highest, right, and then 140 is the lowest. They have real-time tasks, which actually get large time quanta, but they get the highest priority still. This is because the real-time tasks they can actually giving large time quanta to real-time tasks. The thing about real-time is if you can't service a request in a given amount of time, you have to refuse the request. That's usually what people are talking about when you say real-time. Real-time means not that I can service things faster than anybody else, than a non-real-time system. Real-time says is I can make guarantees about how long it'll take for you to run. In other words, how long it'll take before you get serviced again. Okay, so this real-time is kind of more is not hard real-time, but it's a real-time that they can guarantee giving you enough time on the CPU. That's why they do this kind of opposite of giving smaller time quanta to the other tasks and higher time quanta to the higher priority tasks. Okay, but put that aside. There are these numeric priorities inside these, right? And what they do is a system of process with the most credits is scheduled next. Credit subtracted with timer interrupt occurs. So this is the same as what we saw before. If you expire a time quanta, I'm going to demote you. Okay? When credit equals 0, another process is chosen. When all processes have credit 0, everybody starts back at their original credit level. In other words, you start a process, it gets a certain amount of credit based on its priority. Okay? As you run and expire time quanta, you get credit subtracted Okay? Once you exhaust all your credits, you move into this other queue where you're not eligible to run anymore. Okay? And then once there's no one eligible to run anymore, everybody gets their original credits back and then they can start spending them again on running on the CPU. So what ends up happening is you run for a little bit, you run for a little bit, you run for a little bit until you're out of money. Okay? Then you get thrown on the street. Okay? And then once everybody's thrown on the street, they reverse the queues. So now everybody on the street gets their credits back, their original credits. They run, and get thrown over there. So this is like another kind of multi-level type of queue. Okay? So your credits are essentially your priority. Whoever has the most credits gets to run. Okay, so what will end up happening is process with a lot of credits will end up running a lot, and then processes, but everybody will eventually get to run because those high priority processes will eventually spend all their money and get thrown out.
What happens to it? What kind of credit gets back?
It can either be back at their original process, but if I'm not sure about Linux whether it can kind of reclassify you. There are some mechanisms so that once everybody gets thrown onto the street, some of the stuff it learned from the last run, it can reclassify you to kind of change your starting credit level. Okay? But that's kind of done separately. It's kind of you spend, you spend, you spend. But how much money you get in the next one is usually determined by stuff it found out about how you ran the first time. I'm not sure about all the factors that Linux uses. Okay, done. Well, we'll probably spend a little bit of Tuesday talking a little bit more about it, just to clarify. But take a look at your books because there's some. They do have a little bit more detailed examples of some of the scheduling.